Welcome to ninth lecture of the course Corrosion, Environmental Degradation and Surface Engineering. Topic of this lecture is surface degradation mechanism due to corrosive action. And as I have shown with the symbol, the one first obvious question comes, what is a corrosive action? And most of the students have been studying this topic since class 6th. If that was a topic and we have been learning from class 6, then what is the use of again delivering lecture on corrosion action? So, it is important to understand that corrosion, as such we know very well, that is a chemical reaction between a material and its a surrounding that causes a corrosion. There is a serious implication of the corrosion, reason being it reduces the performance, it increases the maintenance cost, and then also it reduces the safety. Major reason is that safety because of the structural integrity and strength. And in one of my earlier lecture, I mentioned that total cost per year in India, which is spent on the corrosion or corrosion resistance, is exceeding 1.5 trillion rupees, which is much more than complete educational cost. So, that is why this topic is interesting. So, another thing is that corrosion, which has been taught a number of times since class 6 standard, but we have a different environment. As we know very well, the corrosion induced surface degradation, because that is our main aim. It is not only the corrosion, but how corrosion induced surface degradation is influenced by environment, operating temperature, and most importantly chemical reactivity of the material. So, if I want to really learn the corrosion, I can't just concentrate only on the chemical reactivity of the material or only on environment or only on the temperature. It is basically a mix of all three. Most of the metals which are corrosive resistant, let us take an example of stainless steel. Most of people feel that stainless steel is a corrosive resistant, it will never ever degrade because of the corrosion. But we can consider, we can show that stainless steel also degrades because of the corrosion. So, it is important, we need to know what kind of environment, what temperature and how it influences. Another thing is that we use the word material instead of the metal, because most of the definition they use the word metal. They say chemical reaction between a metal and surrounding. Well, in this case we have used a material, not a metal. Reason being the non-metal like a polymer, ceramic and composite, when subjected to specific environmental condition, can go through the process of corrosion degradation. Let us take an example. Say there are certain polymers in ceramic, they may swell, soften, dissolve when exposed to the acids. To choose appropriate material for certain application, it is necessary to apply relevant protection measures. Also, it is necessary to understand behavior and degradation modes of the material. So, that is why this course is important. I will just cite few examples. Let us take an example of the sodium, very highly chemical reactive material. You can't leave it in open, it immediately works with the water and makes some sort of other product. It may be salt, maybe like you can fast act with a chloride, make a sodium chloride or maybe other. So, sodium cannot be found easily in open environment. Whenever you leave the sodium, immediately it will react the environment. So, if I make something out of the sodium, I need to really think how to do that and what kind of measures are really required. Let us take another example, gold, platinum. Now, we say these are the noble metals, reason being they are non-reactive, and then most of the time they remain in pure form in a nature. So, we can take advantage of this metal, and then we have observed that most of the electrical contacts are routinely coated with a gold or maybe say the gold like material in industries to stop or prevent the oxidation. Another interesting thing is that we have been mentioning about the corrosion, but there are some metals which have a built-in resistance to the corrosion in form of sacrificial layer to protect underlying the material. In such cases, the corrosion product such as oxide, hydroxide or salt form a thin, adherent, insoluble and capable of quick renewable layer. So, So, I am using the word, it is a thin, it does not change the dimension significantly. So, it is the advantage. It remains adherent to the surface, that means it does not cause a delamination so easily. It is not soluble, insoluble. So, it is not getting dissolved so easily. On top of that, it has a quick self renewal layers. If something is damaged at some location, immediately it gets renewed. So, it has all good properties. So, this kind of metal should be used again and again, but we need to know how. And even in some cases, those materials also may get degraded. So, we need to know those circumstances, right. So, these are the important aspects, and then we use a new category. We say that these materials will act as a passive material in order to protect their surfaces from a further deterioration. Passive material rely on their preventive corrosion products. That means, whatever the product comes as form of the oxide or hydroxide, they are good product. Means we are losing some material to prevent. Is kind of the providing some sort of security on the surface, so that no further corrosion occurs. Another one, we say not all corrosive products are protective. Sometimes we assume that oxide will form and it will be really helpful, not necessary in all the situation. Rust is the name for the corrosion byproduct. We know very well that in iron or steel there will be some sort of the rust formation. So, it is a good byproduct as such, but what is the problem? To understand the problem related to rusting, we can concentrate on this slide, but we have shown 3 figures. In figure 1, we have shown a jaw coupling, and you are able to see there is some sort of a brown color iron oxide on this jaw coupling. The second figure, which is an inner ring of roller bearing, and we are able to see the marks on this. And third one is a bearing of engine bearing, but we are able to see very high corrosion as well as a rust on this kind of bearing. So, rust as such can act to prevent further corrosion, but it does not appear always. That is why we say rusting causes an increase in outside dimension. Now, the dimension are also increasing because of the rust. It is not going in only few nanometer or micron, it sometimes increases beyond that. And another problem with the dust is that it gets dislodged, because the porous nature and the weak tendency to get a stick to the surface, it will cause a dislodging. Now, if this kind of a jaw coupling, if we run at the higher speed, we will find some sort of a rare debris particles are coming out of this surface also. In this case, because there is a sliding along with in the case of the high load, there will be form of some sort of a corrosion and then the wear rate. So, they will get mixed together, and this is heavily depend on a corrosion and a wear. So, in case of environment or there is a water environment and the rust is getting formed on the surface and wear is also happening, that cause a major problem with the surfaces. So, that is why we say that in the case of the rust, we need to really think carefully, reason being if there is already humidity, but in case if there is some sort of a industrial vapor or acid, in this situation some sort of a corrosion of the material will act, because there is an environment or corrosive environment. Humid environment itself is a corrosive environment, and then there is a formation of oxide. We should be sometime happy with oxide, but whenever there is a wear or some other associated mechanism with that, then this kind of a product will be a problematic. So, chloride, oxide, sulphide, and they get formed and maybe they are porous, not getting adhered completely to the surface, will cause a failure or enhance a failure. That is why we say corrosion, mechanical sliding, if we combine together, it will cause a huge wear rate. So, if I consider wear alone, it will not cause that kind of damage, but and moreover if the corrosion alone but is getting passivated, again it will not cause a much problem. Here we get combining these two, it will enhance wear rate significantly. That is a major say that we can say 1 and 1, it does not make it 2, 1 plus 1. Here it was possible, it makes 11. So, we need to really consider whenever there is a need to design a good product or long surface life product. And another point comes, Not only this stops here, the particle, wear debris particle, which are really a product which come out of this the layer, or maybe say this thin layer, if they are getting some wear debris particle come out, and then they will act as a abrasive materials. So, not only it is stopping the corrosive wear, it will act a corrosive abrasive wear. So, it is really enhancing significantly the material degradation. That is why we need to really consider this kind of topic and understand the phenomena, understand the science, and based on understanding of that science come up with a mitigation solution, which is important aspect. Now, I can really, because I have been working in a bearing area almost for 20 years plus or 25 years, we can say the most prevalent sub-assembly found in practically all machinery. So, all mechanical machines or even a number of machines, not necessarily mechanical only, most of the machine bearing is a most prevalent sub-assembly. It most common assembly, even human joint we find number of bearings there. And if this kind of bearings get deteriorated, the most of the performance will be decrease, and naturally we need to change the bearing. That is why we say the cost of the bearing deterioration is very high, is very high. Now, if I want to express in other way why the bearing cost should increase so high, the reason first thing is the bearing need to be replaced itself. The bearing has a some cost, replacement will be there. What is the second one? Is a downtime and a productivity loss. Naturally, when the bearing fails, we need to replace it. This will cause an unscheduled downtime, or maybe we need to stop the machine and change the bearing. And because of that, machine has to stop, and because of the stopping of machine, productivity loss will be there. We may miss some sort of a deadlines, and that will cause a huge financial losses also. And moreover, not only this, even in the starting condition, bearing is getting corroded because of the water ingress or maybe some other acid formation or some sort of the gases. What will happen in this situation? Corroded bearing will increase the friction, because we know the dimensions are changing. Naturally, when the dimensions are changing, some sort of resistance will be there. It will increase the friction force. That naturally that will cause a high energy consumption, and then it will increase the operational expenses also. Again, if we want to really go for more frequent maintenance, because the labor cost will be there, and then whatever the oil change and the other associated parameters will be there, that also will increase the cost. And last one is the safety. Naturally, if the bearing corrosion occurs, safety is getting compromised one way or another way. Not only the safety of apparatus, but safety of the employees also. So, you can say corroded bearing failure could result in accident, injuries, damage of the other component, not only that bearing component, but because of the failure, maybe the quite possibly the gearbox is attached with that also may fail. So, there are a number of failures will increase if there is some sort of failure of the bearing. So, that is why we can say the bearing cost failure is really significantly high, and we should avoid, and most of the time it is because of water ingress, because of corrosion or related phenomena. Now, how to avoid all this? Naturally, there is as I mentioned that there are some material which have a passive nature. What is that? That has been explained in this slide. What we use the word passivation. What is the meaning of passivation? To make a protective oxide layer. And as I mentioned in the previous slide at the towards end, that not every material will make a protective oxide layer. There will be formation of oxide layer, but not necessary that will be protective. And naturally, we need to understand what. Here we can start with aluminum. Aluminum has a very good resistance towards the corrosion, but you can see here if the aluminum is submerged in a hydrofluoric acid, which I am showing a 10% is on the higher side, we can find some sort of scratches, and this scratches is because of the corrosion. So, first thing is that aluminum is not a corrosive resistant completely. It gets corroded, but it makes a layer. That is what we are using the passivation. This passive layer to prevent further corrosion. So, what we can say in short, that due to development of the protective oxide layer, which you can use a aluminum oxide on the surfaces of the aluminum surface, aluminum alloys are widely used in industries, right, and we can say they have exceptional corrosion resistance. In true sense, they do not have a resistance. 1 or 2, maybe say few micron or nanometer layer thickness will be there, which will be corrosive layer. So, it is not a aluminum, it is a aluminum oxide which is getting formed on the surface, but that is making kind of passive layer. Once a layer has been made, further substrate will be stopped or maybe will not be exposed to the oxygen, and then it is impermeable, or we say that oxygen cannot find a route to the substrate and it will not really corrode that. We can say this oxide layer serves as a barrier. Now, I can say that this is a chemical barrier, or I can say this is a kind of 1-2 layer, that means a physical barrier. It depends the way we want to present. We say that this acts as a barrier to prevent underlying metal from corroding further or further oxidizing it. So, it prevents further oxidation of surface, and that is why we can say in from that point of view aluminum is a corrosion resistant, but it is not in true sense completely corrosion resistant. It is not a noble metal the way we discuss about the platinum, the way we discuss about gold. That is why we say it is good, but it is a low cost solution, and if we are not worrying too much of a high significant change in the dimension, or maybe say in the few nanometer or few micron layer, then aluminum is a good solution. But we do not want any change in a dimension, then we need to go for the noble material. So, aluminum is not a noble material, it gets corroded, but because of the passive nature of that layer, it is useful to us. Another one, we use the word self healing. We say if protective oxide layer is damaged or removed because of one reason or other reason, maybe the suddenly in between sliding occurred or increased significantly, or there was some sort of a fluid induced removal of the layer, that is a possibility. So, we can say in the situation aluminum alloy can spontaneously reform the oxidized layer or oxide layer in the presence of oxygen. However, we need to see presence of oxygen should be there, and maybe machine if it is operating very high speed and then oxygen is not available sufficiently to reform the layer which is getting removed from a surface, and then reformation there is some sort of gap, then again aluminum will not be able to resist the corrosion, and there is a possibility. So, we need to really think about all those parameters. However, for the time being we are assuming that if the layer is removed, it has a self healing properties, it will be able to form oxygen, assuming there is abundant oxygen available. However, we think about a space, naturally in a space oxygen will not be available, the self healing properties will not be available for the aluminum. However, for time being we are assuming in normal environment and oxygen will be available, and then there will be repairing possibility, we can say the aluminum repair themselves and maintain the corrosion resistance. So, these are the aspects which are important to understand. We picked up this example from 2006 reference, SUSE the SJ, which has been mentioned. If you want, you can read this paper. Now, we have started discussing about the passivation. We want to give a little more the emphasis on passivation. We say we can show that there is an amount of the corrosion, and the way when we consider the aluminum example, we can say in an aluminum there will be with the time there is a possibility initially the corrosion will occur, but this corrosion is continuously decreasing in the situation. So, this black color line which I have now made a red color can indicate a passivation, that means slowly it is coming to the 0, and this is the total amount, it is not the rate of the corrosion, it is total amount of the corrosion on the surface. So, this is a passive case. However, the few cases like we consider some sort of a rust, that is a active, it does not get prevent and stopped at all. So, the rusting in the situation is active corrosion, and in this active corrosion with the time this layer will continue, this will continue on the linear curve or maybe the non-linear curve, depends, with the time it will continuously increase. And you can see that now there is a gap, if the passive layer has been made, then it will be always the better one, and then if we are not able to think about or provide a passive layer, then this active corrosion will be major problem, even it can eat away complete material, that is a possibility. So, we can express this in a word, but we say the most corrosive film passivates or cease developing beyond a certain thickness. So, once it reaches to the thickness, it stop corrosion, or maybe the layer is sufficient, and then to act as a barrier for the further oxygen, and it does not allow oxygen to react with the surface, which is important. Sometimes people feel that this is a dirty color or maybe the red color, we should clean it. That is a major mistake. They should not clean the surface, reason being then in the that situation the oxide layer also will get removed, and the quite possible the coefficient of friction may increase again, wear rate will increase again. So, the science is important from that point of view. Another one is the useful as a rusting process comes to the halt. Now, here using the word rusting or corrosion, like many times we use a word, there is a possibility in some cases environment can be stopped, or maybe the water decreases, or maybe there is some sort of component which under good compression or pressure. So, it can this kind of a phenomena can be halt on their own. That is what we are using the word self and then the stopping or the passivation process. However, if the corrosion films are the brittle, porous, now by using the word that surface or layer which is getting formed because of the corrosion is a brittle, or it is a porous. If the porous, then naturally the oxygen will keep passing from top surface to middle surface to the bottom surface. In this situation, then this sacrificial or short lifetime corrosion film will be lost, and is not going to give a good solution to us. Naturally, if this is a situation, we need to think how to generate other barriers, how to generate additional barriers. So, we do have a number of process what we call a chemical passivation. We can think about a conversion coating, or we can think about some physical barrier. So, there are two chemical routes, one physical, and maybe there may be many, because this is a research topic and people keep doing a lot of research in this area to prevent the corrosion one way or another way. Let us see what is the meaning of the chemical passivation. We are using the word nitric acid or citric acid solution. If used, then it can stop the corrosion. Initially it will corrode the stainless steel, but further it will not allow more and more corrosion. And in number of lubricant, this kind of chemicals are added into the lubricant itself to make one passive layer on the working surface to prevent corrosion or to further corrosion of that. So, we are intently making corrosion or inducing corrosion on the surface to prevent further corrosion. So, that is a science, and we need to understand, because we require a perfect balance. Naturally, concentration is important, and then with the time that concentration will keep depleting. So, naturally we need to change that lubricant, that kind of media, maybe after 6 months, 9 months, depends on the working condition. So, this is what we are showing here in case of the stainless steel. When you think about the nitric acid or citric acid, that can really passivate aluminum stainless steel the surface, and then they make a top layer as a chromium rich oxide layers. So, in earlier when I started this lecture, I say very clearly, many people assume stainless steel is a corrosion resistant. Whatever you do, it will not really cause a corrosion. No, it is not. We need to think how to prevent the corrosion of stainless steel. Naturally, here the one of the treatment has been mentioned, the nitric acid or citric acid. We need to use a solution to, so the layer is formed, and then layer is a chromium rich oxide layer on the surface that prevents further corrosion of that. Now, coming to the conversion coating, we say another one possibility to prevent the corrosion is that we can do a phosphating. That means, if the steel we put some sort of phosphate is X, and sometimes also solid lubricant on this, or even aluminum we do anodizing, which is a common process. So, I am assuming the aluminum is a good resistance, wear resistance, or maybe it is the corrosion resistant, but we do anodizing so that further the layer should not get a corrosion. Only the top layer, which because of the anodizing, there is some sort of a film formation and which adhere to the surface, and further it should be avoided. In this case is that this anodized layer is thicker, not a thin the way we indented, but slightly thicker, but stronger, and then it is much more wear resistance compared to the other oxide. That means aluminum itself has a layer, but that layer what we are mentioning in this case is not sufficient to prevent or corrosion. It is not as good as an anodized layer. So, it means if there is some sort of a corrosion environment, and then aluminum itself is not able to handle the situation, or maybe aluminum is not able to make that kind of oxide layer which is causing a stopping of the corrosion, then we can think about anodizing. So, these are the levels where we say that aluminum can, in ultra mild cases, it can act as a corrosion resistant, but as maybe in case of the some sort of acid and all, there is a possibility to increase corrosion of the aluminum. In the situation, we should go ahead with anodizing, which is another conversion coating method to generate a barrier to stop the corrosion of aluminum itself. Now, you have come across a number of physical barrier. We know that we do a painting on the materials, or maybe sometime we do some sort of a polymer films on the surface to shield the material surface from corrosion. So, these are the physical barriers. We put another material on the surface and then apply physically. Maybe if there is a covalent bond or chemically attached, then we can say those are the chemical layers. If it is only physical kind of addition to the surface, then we will say these are the physical barrier. So, this topic is very interesting from this angle to understand the corrosion and understand the even what we say, that we cannot say that this material is a corrosion resistant. Quite possible we need to mention about the temperature, and we need to mention about the environment also. All three together will make will provide that whether there will be material will be able to sustain corrosion, or maybe will be acting as a corrosion resistant or not. Now, we will try to understand a few more phenomena. What we call in this case is the intragranular corrosion. In one of the previous lecture, we have mentioned very clearly that most of the brittle material fail because of the weak granular boundaries, and that is the same thing here. If the grain boundaries are weak, quite possible the corrosion will dominate. So, just to differentiate here, I am showing here there is a surface corrosion, and you can see there is a this corrosion is going deeper and deeper in surface. So, in this case is intragranular kind of the corrosion, which is passing because the corrosion requires some sort of route how to pass, and that is intragranular boundaries or the grain boundaries, because being weak boundaries providing a good path for the corrosion, and quite possible whole chunk will come out, make a pit, and that will be called a pitting corrosion in this case. So, not only the surface corrosion, there is a possibility that passage has been provided by the weak boundaries, and then corrosion progress inside, and then maybe whole chunk will come out, as I say the pitting possibility is there. So, what is the meaning of this as such? If you want to express in a word, we say the IGC occurs around the edges of grain, and grains are what is the boundaries or the borders between the crystals in polycrystal material. Now, again we are bringing an example of a stainless steel, which we say earlier that it is a corrosion resistant steel, but here we say there is a vulnerable to IGC. So, intragranular corrosion, it is really possibility is there that stainless steel surface or maybe the material gets a lot of corrosion. We say the reason being that because the corrosion resistance decreases particularly at the grain boundaries. So, we need to think materials which are known as corrosion resistance, what is their grain formation and what are the grain boundaries, and whether the corrosion will be resistant, those boundaries will be corrosion resistance or not. If it is not, that what kind of treatment is really required in those cases. Now, another case we can say that last time we were thinking about cooling, tampering was a word we used, that you can increase the temperature to release the stresses, we do a tampering, but it also causes the precipitations. And if the precipitation is near grain boundaries, naturally the grain boundaries will be weaker, and then there will be problem. So, most of the alloys during the cooling time, they find this kind of a problem, and naturally the corrosion will play a major role there. So, that is again a case of IGC. Now, another one is what we are mentioning, that the temperature here. If there is a temperature on the higher side, this becomes a very fatal and a major concern as such. At a high temperature, we know the recrystallization happens, the resoftening happens, and then there is a possibility of more and more grain meeting, and then grain boundaries are possible to become a much more weaker compared to the lesser temperature. In the situation, there is a possibility of the local pits or crevices and maybe the bigger crack or fissures, and then it will cause a IGC in this case. Now, why we have been using this word again and again? We say IGC is a major problem in many industry, most important industry like oil and gas industry, chemical processing, most of the chemical processing industry, they are important, and then the water related or maritime industries. When we think about the ships, we think about the boats or maybe related we say that robots, then we need to think about IGC, which are important, because IGC will play a major role there, and then it finds some sort of weak boundaries, and then corrosion will occur across those boundaries. Now, to elaborate this, what the Lee et al. Did a number of experiment, and what kind of experiment they did? They use a low alloy steel. Again, in previous slide we said if you increase alloying, there is a more chances of the failure, more chances of the grain boundaries because there is a weaker grain boundaries and corrosion is possible. So, they did experiment on the low alloy steel, but they use a word S500 AW, and then they wanted to test this corrosion microstructure, and they did some sort of immersion test. In this immersion, the solution pH was kept around 4.5. Naturally, it is an acidic site. And then because of the acid formation, corrosion will be dominated, and then after that maybe they kept for the some duration. In this case, we are showing the 4 figures. In the next slide again I will show the 4 figures. They observed after dipping for maybe 0.5 hour, 1 hour, 2 hour, 3 hours, then they wash it, and then they use a SEM examination, and SEM imaging are shown here. Naturally, this is after 0.5 hours. And this is for the 1 hour, this is for the 2 hours, and this is for 3 hours. So, what they mention very clearly, there is a ferrite grains, because the steel is there, so ferrite will be there, and there are grain boundaries we are able to see. And then what we are able to see that up to 1 hour we are not able to see that kind of corrosion. So, precipitation phase, reason being a precipitation, we say precipitation phase, grain boundaries and corrosion after 1 hour of immersion are noticeable. That means, up to this not that much noticeable, but you can see these are the 2D figures, but here we are able to see some sort of a depth also. So, in the figure C we are able to see depth, in figure D we are able to see the depth. There is a possibility of the kind of the pit formation, there is a possibility of some sort of the pits as well as the grains, and then we are able to visualize kind of 3D. That is why we say the ferrite grain and ferrite in perlite area both continue to get corroded. So, there is a insight, now the depth is also coming, it is not only surface, and that is what I mentioned in intergranular corrosion, there is a depth which is also getting corroded, or maybe the vertically there is instead of horizontal spread of the corrosion, there is a vertical deep corrosion also on the surface. So, and then what we say that this kind of surfaces are more and more visible, and then here the precipitation phase, which is what we are using, the iron carbide or Fe3C is being the more and more dominating at the surface. So, here at least in this image I am able to see much more deeper thing, and if depth is increasing, naturally a big chunk will come out, and that has been shown in the next image. You can see here the E has been shown after 12 hours, F after 24 hours, and this G 48 hours, and H 72 hours. And now here you can see a complete dip which has it there, and maybe if you are able to see, these are the increasing from 2D to 3D, and finally a chunk comes out, and then which is the dip is visible in this case. So, what we can say here, after 48 hours of immersion, then it started to showing up showing up on the sample surface due to the precipitate phase or the Fe3 phase and the grain boundaries, and after 72 hours precipitate phase of the grain boundary came off. So, it is a completely kind of dislodged from a surface, and then it is really increasing in a size also, and then it causes a numerous dents on the surface, and this is a kind of initiation. Actually other associated phenomena will take place, will cause a failure. Now, just to show this complete phenomena schematically, we are able to show this kind of figures. We can say there is some sort of steel here. Now, there is some solution, and then solution contain the HSO3 as well as a hydrogen, in this case ion. And then what we are showing, this is a precipitation, that means the blue color is showing the precipitation, here also the complete precipitation, this is precipitation happening, and that shows the precipitation, the black color, this one it shows a path. You can see here the pit formation over here, you can see the deeper pit formation over here, deeper pit formation here also. So, this is schematically not true, but whatever has been we have learned from SEM, that we are trying to depict this, and this everything has been taken from this reference. They have provided complete detail about how they have performed experiment, what kind of a technique they have used for the sustainability or repeatability of the results, and that has been explained in this part. This is a very good example to mention what is the IGC and how really it is going to damage the material. If we do not consider, then quite possible surface will not be able to see the failure, corrosion is not spreading that much, but maybe vertically down, or maybe that was a depth, there is a huge corrosion, and then whole material will fail, maybe say in a short duration of time without much notice. Now, we have given a kind of overview what is the need of the corrosion, what is the need of this topic. Well, let us look at some sort of important, what you say, that most prominent types of the corrosion, that is corrosion and their mechanisms. So, we are not going to cover all kind of corrosions, maybe you go through the number of books, and there are handbooks also which are covering corrosion in maybe say number of classification. We are not going to cover all kind of a corrosion, but most prominently which all is causing us kind of a surface degradation. We will try to discuss on a few mechanisms in this. So, what we say in this case, basically main major bigger domain is the three main type chemically induced corrosions. One is called aqueous, second is a high temperature, and third one is a biochemical and biological. As in earlier my lecture I say, we will not be dealing with the biology. So, biochemical has been removed from our course, and biological corrosion also has been removed from our course. So, we are not going to discuss about those. Now, remaining two, aqueous, and the aqueous is one of the popular kind of the failure is a rusting, which happens in most of the iron or iron alloys. And then there is aqueous also happens swelling, as I mentioned earlier, that there is that happens also in case of the ceramic and cements, or maybe the concretes, and that what we call as a softening process, but that happens in case of the aqueous or water environment. There is another one, high temperature. As we know very well that the temperature increases, energy increases, chances of chemical activity will increase. So, it can be oxidization, sulfurization, chloridation of the metal, and even some sort of ceramics, solvation, and or formation of the salts. These are the major kind of so the big two classes. And then what is really the environment, what kind of environment? We say there is maybe acid formation, or maybe the acid availability, or salt water, or water itself as such. This kind of media or liquids can really damage material surfaces, or we can damage the metal and non-metal surfaces. Now, when you think about economics point of view, as in earlier lecture we say that it causes more than 1.5 trillion loss to the India every year, naturally economic losses. We say the aqueous oxidization of metal at the room temperature or slightly at a high temperature, and then what we use the word high temperature corrosion. They are the two important type of the material breakdown caused by chemicals, including this case chemical. Here I am using the water also as a chemical, I am not keeping away from a chemical. So, it is also acts as a chemical, and then this causes a huge loss, economic loss. So, there is a need to really understand what are the prominent kind of the corrosion, what kind of the corrosion mechanism, how do we prevent this kind of mechanisms. So, let us look at the classification of the corrosion. We can see the corrosion classification can be done. As I earlier in the previous slide I also mentioned, microbial and fungal correction or maybe corrosion type we will not be covering in this course. However, in the bigger domain I can say I will divide this corrosion into 5 categories. First category is something like a uniform corrosion, galvanic corrosion is second type, pitting corrosion, and D one is a crevice corrosion. Here I am separating the pitting and crevice the corrosion region being the characteristics are slightly different. And I have given another kind of a corrosion what we call as a stress corrosion cracking SCC, and these are the 5 types of a corrosion we are going to really cover in this course. Now, uniform corrosion, why we are using the word uniform? Because it really does not look at only one particular portion. If the surface is available, then this kind of corrosion will occur uniformly across a material whole surface, complete surface, and rust is one of the uniform corrosion. Aqueous corrosion is also one of the uniform corrosion. Now, coming to the galvanic corrosion generally we require the 2 different materials. In the aqueous corrosion even one material is sufficient, but galvanic corrosion we require 2 different materials. Now, they need to act, the material need to act electrochemically. If you remove the electrolyte or maybe media in between, naturally the galvanic corrosion will stop. So, that is what we really require, electrolyte presence is important. Now, coming to the pitting corrosion, it does not happen in one go, it takes cycles, it takes number of cycles, maybe say and then number of hours to cause of pitting failure, and that will be discussed in this case. It is basically kind of cyclic phenomena we need to think from that point of view. That is why we are going to give emphasis on repetitive conditions. Crevice corrosion is something like sometime there is some sort of hole or some small passage or even like surface some sort of damage, and then the localized corrosion happens there. What we say that it occurs in small crevices, and then where the oxygen or corrosion inhibitors do not have access. Many times in the lubricant we provide oxygen inhibitors or corrosion inhibitors, but even in those situations that this kind of corrosion will occur, because this kind of the inhibitors will not be able to reach to those locations, and then it acts like the way we have shown in previous slide IGC. Similar kind of phenomena will occur. However, we will say that it can occur beneath the surface also, and then beneath the deposits maybe the top surface is not available, but there is some passage available and corrosion follows that passage. So, it is basically localized corrosion. And coming to the last E, when we say the stress corrosion cracking, we say this is the type of corrosion caused by the interaction of specific media in corrosion environment under the tensile stress. Maybe there is some sort of a tension or tensile stresses which is trying to crack it, trying to elongate those surface, and those surfaces being a weaker in tension will crack. If there is a cracking, naturally the next surface will be exposed to the corrosive media, naturally it will continuously increase. So, this is what I plan to divide into 5 categories. However, I have come across a number of references and number of books where they really go ahead the more number of classes. I am just taking one of the example. In this one of the reference book says that it should be the general corrosion. General corrosion and uniform corrosion is by and large same. Galvanic corrosion we are also going to explain. Localized corrosion, we say instead of localized corrosion I will go for pitting and crevice corrosion to separate categories. Then there is another one, they divide something like a flow assisted corrosion, as instead of thinking of the flow assisted corrosion as such a single device, a single mechanism, I will consider this as a erosion corrosion. So, erosion we have already considered earlier classes. Corrosion, once we complete this, we will may cover this topic in lecture 11, where we are going to go at the synergetic effect of the different mechanism of the surface degradation. So, this topic is for the lecture 11, not a kind of only the corrosion, because corrosion naturally if there will be be any mechanism will cause the corrosion, and if there is a fluid at some flow is some velocity is going to impinge, naturally that will take away the layer. So, making a special class a corrosion or erosion corrosion, or in this case a flow assisted corrosion, I feel that may not be really required. Another one, we are using the word environmental cracking. Instead of that, we have said that stress corrosion cracking, because under tension we require environment corrosion film will be there, but if it is not subjected, to the tension, cracking will not be so easy unless the material itself is going to be like that, like a rust. Rust maybe is the relatively weaker and then it crack its own. So, and we are covering this rust in aqueous corrosion or uniform corrosion. So, we will not repeat over here. Last one, they mentioned about high temperature oxidation. So, in earlier lecture I said the oxidation is just sub class of the corrosion, and then naturally the high temperature everything will change. Even uniform corrosion will increase, galvanized corrosion will increase, pitting will increase, stress corrosion will increase. So, separate category on high temperature oxidation, I believe that it may not be that much important. So, that is why we are going to stick to the classification in a 5 category. Now, if I want to express in some other words, what we can say is the most frequent type of corrosion is a general corrosion. As such, what we are using the word uniform corrosion, and then what is really happening in this case, surfaces will get rougher and rougher, right. So, general corrosion, uniform corrosion, aqueous corrosion can be kept in the same category. Necessary that people juggle with the words, using the word, these are the kind of synonymous. Now, coming to the localized corrosion, generally occurs in isolated area with the rest of the metal surface largely is untouched. This is only the some specific area, and what we are going to cover with the 2 topic, pitting and crevice corrosion. That is what we can say, pitting and crevice corrosion, which we are going to deal, is equivalent to localized corrosion. When we say that when chemical as they grow and attack the surface or metals, the corrosion is going to infuse also by microbes. However, we will not be covering the microbes or microbiological related corrosion, we will not be considering in this case. Next one, as I mentioned, the high temperature oxidation takes place at the high temperature, where the predominant interaction is between the metal and reactive gas or molten salts, but this is not going to make another kinds of the class of the corrosion. It will, whatever we cover in different class, everywhere the high temperature is going to affect, enhance their rate. So, not necessary we need to be considering this as a separate category. Another one I mentioned, the environmental cracking is caused by the combination of the corrosion and under some sort of additional phenomena. It can be tension or some kind of the wear phenomena or mechanical strain. So, again we are not going to consider this as a separate category, and better we consider only this cracking under the stress condition and the tensile conditions. And if it is happening because of some other reason, that will be like, if there is a mechanical sliding on that, actually we are already covering in the wear, so that will be considered. So, we do not want to increase the number of classes. I assume the 5 classes or 5 subclasses are sufficient to cover the corrosion, and then if we understand this, a combination can be any. So, 5 combination can be used, and then we can generate a number of kind of corrosion phenomena. However, we need to really think about basics and then how the corrosion occurs, so that we can utilize that science, that knowledge for betterment of the product design. Let us start with the first one, the general corrosion. However, now in this case particularly we want to give emphasis on the rust, which is causing a lot the failures. What we say in the rust, we require chemical action, we require material, we require environment. If environment is not there, this kind of rust will not occur. If material is not there, again it will not occur. If there is no chemical action, again it will not occur. So, we require all, and then sometime we use the word rust, sometime we use the corrosion, sometime we use the word oxidation. Again they can be played in manner. Now, here we are showing some sort of the alloy of iron, the clean surface, a started surface. Now, in this situation we are showing that this surface can get oxidized in presence of oxygen, and it will make a iron oxide or ferric oxide. Now, this ferric oxide in presence of water, it will give a hydrated ferrous oxide, and that is what the red color has been shown over here. So, if I want to define a rust, we can say the rust is a byproduct. So, red color what has been shown in this case, or the brown color which has been shown on the surface, which is kind of the porous, and that can be removed easily, rubbed easily, and then the powder will come out of this. We say it is a corrosion byproduct as such. So, even though we are using the word rust, it is just a byproduct of the oxidation and in presence of the water, the product which comes out. So, this the corrosion byproduct that develops in iron or iron and steel, or maybe is alloys of iron. Now, rusting is aqueously assisted, it happens in presence of water. If you remove water, this complete action will remain only here, and ferrous oxide is reasonably good the surface, oxide surface. However, if causes an additional the phenomena, wear phenomena comes, then it is a problematic. Otherwise, it is not a problematic. If you do not touch the surface, if you do not remove the surface the iron oxide, it will the life of the component will be on higher side. However, because of the hydrogen or hydrated ferric oxide, then it is completely giving a path to the go for the depth and then go for the more and more corrosion. The way we have mentioned and discussed something like IGC, same thing happen in this case also. So, rusting is a aqueously assisted form of the corrosion. Rust is characterized by formation of outer layer that are predominantly made of a hydrated iron oxide and typically have a reddish brown color. Now, there is another one what we call as a magnetite, which is a darker in a color, but then maybe this surface, and on the top of that there will be another surface which will come as a magnetite, and then there is a closer to the metal surface, and top is kind of the porous layer. That is what has been mentioned in this case as rusting. We required a chemical, we require material, we required environment, and then this is a process. Iron oxide, if you remove the water and then go without water, this process or this kind of corrosion can be reduced significantly. Now, to explain this why water and all, I am using this kind of sketch. We can say assume this is a iron or iron alloy bulk on the face, while on the top surface there is oxide, maybe iron oxide itself. However, there are some sort of salt crystal or some sort of contamination, is some sort of irregularities on the surface. Suppose there is some irregularities on a surface. Because of the irregularities on a surface, there will be some sort of a cell formation, and that how it forms, I am going to explain those. But before this, as I mentioned, this is a oxide layer, this is salt, and this is a what top surface we are using in the place of the water or electrolyte, it will act as a cathode. So, this cathode formation around the contaminants will be more dominant. And what is the cathode? We say is basically transferring electron to the oxygen, and from where this electron will come, naturally that will come from a bulk iron. If it is coming from a bulk iron, naturally this is going to act as an anode. So, that is why we say there is a cathode and anode, and a water is act as a electrolytes. So, there will be continuous loss of electron and continuous deposition of electron. So, this is the kind of the battery action happens, but because of that this bulk iron becomes invisible and everything will now be this kind of orange. So, this orange will continuously increase in the depth, and then finally we find everything has gone completely, and that has been shown to some extent in this figure. We can see here that the crack formation, because this kind of a layer is relatively weak and then the porous, and then it gives a sufficient space for the ingress of the water path of the water to inside, and then there is some sort of a pit formation. So, it is helping to form the pits, and that has been shown in a bigger way in this kind of example. You are able to see this is a kind of iron alloy and subjected to this kind of a rust, and there are the deep pits also in this. So, that is the mechanism has been shown over here. Now, if I want to express, we say that in this case water or aqueous solution function as a electrolyte. What is electrolyte? It facilitates electron movement, increase, and if I remove this electrolyte, there will be stoppage of the corrosion or maybe the reduction in the corrosion rate. However, we are saying it is in presence of this electrolyte, the water and then the corrosion rate is increasing, and then it also allows some sort of a small electrochemical cell formation and this is where if there is some sort of a discontinuity and maybe some sort of pit or maybe some sort of crack, it allows to form a kind of electrochemical cell and then maybe accelerate there, and then this kind of what we say, in presence of oxygen and electron and ion, this process will be much faster. And this is initially this surface, the oxide surface is very thin initially, as progress happens it becomes accelerated, or initial failure will not be that we say it goes as with a non-linear behavior. It is not really going with a linear behavior. Initially I showed one diagram where we show the passivation and active zones. So, in this case it is not linear, but it is going to increase rapidly. Why rapidly? Reason being that slowly the cathode area is going to increase significantly, anode area is going to reduce. We will explain later in the slide with example what is really impact of that, but for time being we can say the smaller cathode dimension will be always preferable. If the dimension of the cathode is smaller, lesser, then corrosion rate can be kept in a check or maybe reduced, or rust can be reduced. However, if the cathode continuously increase, then this rusting will increase significantly, or chemical corrosion will increase again significantly, and that is what there will be problem. However, this bulk iron, as I already mentioned, that act as the anode, and anode formation beneath the crystal are contaminants. So, whatever wherever is the contaminants are there, and basically it is the oxidation process, reason being material loses an electron from and then it allows to get into the solvent or maybe the solution as such. So, this is clear, the rist formation, crack formation, and then we are saying that pit formation is also there, which will be having some sort of iron ions, maybe sulfide ions are also possibility is there, and as I mentioned in this case. So, overall this is a mechanism how the wear rate increase and how the rusting increases, corrosion increases with the time. Initially it may be slow, but nonlinear curve will occur, a reason being the cathode area is continuously going to increase, cathode dimension are continuously going to increase, while anode dimension are continuously reduced. Now, we continue this topic, what we are saying, the rusting and then maybe we are relating with aqueous corrosion as such, reason being if water is not there, rusting will come down. So, what we say that when exposed to the water, what is really going to happen? The metal surface develop a thin layer of the water molecule. Why? Because most of the metals they have a wettability. If you put a water on the surface, it will spread, it will make a thin layer. If you want to avoid this kind of rusting, make a metal which does not allow water to stick. Now, the many people do coating in a manner the water does not stick to that, and it makes like material where the water droplet remains as a droplet, it will not spread. While in this case we are assuming it is going to spread as a thin layer, and once it is done, what is going to happen, that there will be ionization of the water molecules, and there will be hydrogen plus ion or the hydrogen ion, and there will be OH also, that will be hydroxide ions. Now, this in addition to that, there will be ionization of the metal surface also, that means metal and the ion will be formed, it will be discharging electron and it will be putting in the surrounding water. Now, because of this metal ion which is a positive and hydroxide ion is a negative, it will get attracted. So, attracted to the negatively charged hydroxide ion, metal ion will combine to form an insoluble metal hydroxide. That means, ultimately we are losing the material from a surface, and this is insoluble metal hydroxide formation will occur, and that we are going to lose the material or maybe the surface depleting the metals from a surface. It will become uneven, particularly uneven is very bad, and there is a rolling motion or even a sliding motion, and we call this the uneven pitted surface. Now, this is the case of the water. Now, here aeroplane I am showing, it is showing that it is going to accelerate under this circumstances. This is a common normal case as such. Now, in case of the acid, in case of the salt which are very corrosive, then because of the change in environment, the corrosion rate of the metal will increase significantly. So, speed up. right. Maybe we are talking about some few kilometers per hour, now we go with a much higher speed. Same thing, the corrosion rate, the whatever that it was taking time earlier, it will take 1/10 of the time, right. So, what we are saying that because of the chemical process between metal and electrolyte happens more quickly. Now, this was only the acid environment, now we are talking of the temperature also. So, if you increase the chemical activity of the electrolyte, corrosion will increase. If you increase the temperature, because energy is going to increase, the corrosion rate is going to increase. And last, we say if you really reduce the pH value, which may be somewhat related to acid formation, if you reduce the pH value, then the corrosion rate also will increase, right. So, if the pH value is decreasing, temperature is increasing, and it is going to really increase the corrosion rate. So, we need to really look at the environment, look at the solution, what kind of solution we are using, and how can we really put some sort of barrier to prevent the corrosion or the rusting in those cases. Now, that is why we say the green color, we say utilizing corrosion resistant metal, applying coating like this is what we have already discussed about the physical barrier like a paint, or anodizing the material to protect the metal surface, or some sort of corrosion inhibitor which we use mostly in grease or lubricant, the corrosion inhibitors. It will really help to prevent aqueous corrosion, it will help to reduce rusting, and it will increase the life. So, this is what we want to explain. Sometimes there is a need to explain also what is the difference between rusting and aqueous corrosion, right. So, that is why this slide I have made especially for that, to indicate what is the difference between the rusting and aqueous corrosion. So, what we say, aqueous corrosion and rusting occurs different conditions, mechanism is slightly different. Now, if I want to define a rusting, we say rusting is corrosion of iron and its alloy steel, right. Now, rust is a byproduct, as I mentioned earlier. Rust is an oxidation reaction that occurs when iron oxygen combine to form iron oxide. Now, iron atom in this case is a process which we are explaining, loses electron to generate iron 2 ion. This is the iron 2, the Fe2 ion. Now, that has been mentioned, which interact with the waters to fire and to form iron hydroxide, because we know that the hydrogen and the water also makes a hydrogen ion and OH ion, and then the hydrogen and the hydroxide is a free, and then there is a positive charge and negative charge, naturally it will make some sort of iron hydroxide. Another one is coming here, iron 3 ions also are formed, reason being oxidation of iron by oxygen. So, there is a one is interaction with the water, and another one the interaction with the oxygen. So, if you break any of this, rust will not be there as such, but because of these two, that is why we are seeing that it is a hydrated form of iron, and that is what has been mentioned. So, this is a form of the rust. If I do not have this product, all other can be aqueous corrosion. So, that is why we have kept a special category of the rust, reason being it happens very commonly. Iron and iron alloys have been used extensively for the number of products. Now, the time has changed, it has reduced to some extent, but otherwise there is a big the number of alloys are related to iron, and then that is why this kind of the separate category for rust is important. So, if I do not get this kind of Fe2O3 or maybe with the water molecules, then we can say the rust is not going to be there. Now, coming to the corrosion, we can say aqueous corrosion is a more generic term, rust is just a subdomain or subcategory of this, that refers to the various metals and non-metals also. It is not only the metals, non-metal also can come. And then there is another environment, is a water based environment. So, water is there, the metals may be different, I can bring a zinc, I can bring a copper, I can bring some sort of polymer that can be in a aqueous can be brought in aqueous corrosion, but will not be part of the rusting. Rusting we want to keep as only as a special one, that iron oxide with a water molecules in this case, or hydrated iron oxide. So, we know in this case, as I mentioned, that it includes a corrosion process involving metals other than iron, it can be aluminum, it can be copper, it can be zinc also. Now, how this aqueous corrosion can be defined? We can say it works on the principle of electrochemistry or concept of electrochemistry. There will be anode formation, there will be cathode formation. These again are the same, the way we have discussed in rust. However, that iron is been removed, now we can bring some other metals. Like in this case, we are saying the zinc and copper metals. In this case, zinc alone can be used, copper alone can be used, now can be mixed also. Now, this is next slide on this. Now, what we say in aqueous corrosion, there is a naturally some sort of initiation. Initiation happens only when there is electrolyte, and in terms of the water with some sort of a dissolved iron, that is what acting as electrolyte, and surfaces of the materials are also important. There is a electrochemical process, the way we started, we say the electrochemical process is important for us. That is why I say as a different regions of metal surface having varying potential, even the metal reactivity is different, their potential difference will be there, and then that is why we say that there will be two surfaces. One is an anode where the metal will get dissolved, it will lose electron and then ions will be formed. Other surface will act as a cathode where the reduction take place, or maybe the oxygen is joining the electron is joining the oxygen as such, right. So, these are the creation of cathode, creation of anode, and exchange of electron or balancing of electron. We use the word balancing of electron will occur, and that is what we electrochemical action, and then there is a presence of electrolyte, particularly water, and with some sort of dissolved ions whichever there, that will be called aqueous corrosion. So, aqueous corrosion is a bigger domain, and then what we are trying to show, you can see in this surface as such, anode and cathodes are shown as same surface. One is acting as a cathode which is losing the material. So, this is a portion where it is loss of the material, loss of the electron happens, and this is a surface where the electrons are getting captured or with oxygen, and the reduction phenomena is happening over here. So, there is oxidation here, there is a reduction over here in the same surface, and we can show this reaction as such. In this case, we are showing a kind of zinc, it loses electron. So, zinc ion here. Now, this electron goes to the cathode, and there is some sort of water ion there, and it acts with water, and then it mixes some sort of this ion. So, this is a continuous phenomena, that is why we say the reaction of the anode, metal loses electron at the anode, and it gets that electron gets dissolved in electrolyte to, and then finally metal ion gets formed or produced. While in case of the cathode, because there is a now unbalance, to make a balance naturally electron need to be absorbed, and then that is why the reduction reaction occurs with the cathode, and this it gets act with oxygen and maybe with some sort of associated ion there at the cathode, and it will cause a balance of this. Now, this comes with the zinc as I mentioned, and there is another one what we use sometime, then in the ships and all we use aluminum, because aluminum has some sort of passivation. While aqueous corrosion, if there is a passivation occurs, that is a good. If it is not happen, then we need to worry, we need to think about. And that's why many times when some books they try to explain aqueous corrosion with this kind of diagram, or they say the copper, zinc is there, and then the zinc is losing the electron, copper is depositing the electron, and that is why the surface gets damaged, because there is a loss of the material, because of the losing the electron naturally iron will come and then it will get dissolved into the electrolyte, and then this chemical process will be continuous. However, the question comes when we think about this, is it not a galvanic corrosion? In my view, whenever there are two separate metals coming, two separate materials is showing in this kind of diagram, that is a more like a galvanic corrosion. However, in this case media can be water. So, I can say the galvanism is a part of the aqueous corrosion. However, we want to differentiate it very clearly. We say aqueous corrosion will be keeping separately, galvanic corrosion will be keeping separately, and then we are trying to highlight the what are the difference between the galvanic corrosion and aqueous corrosion. In my view, We can say aqueous corrosion, which is also known as a uniform corrosion, is a type of corrosion that affect the whole surface of metal. The process is repeated until the metal is entirely corroded, or it is protected by some sort of passive layer or some additional barrier layer, something like that. And then environmental variable in are something like temperature, acidic nature or pH values, or some sort of contamination which can really increase the aqueous corrosion. So, these are related to the aqueous corrosion. Coming to the galvanic corrosion, we say galvanic corrosion occurs when the two different metal or alloys are electrically linked or submerged in an electrolyte. So, even I can operate with a battery also, I can create a potential difference there, I can start galvanic corrosion. Or if it understand, then I can understand the why in some the material pair we find the galvanic corrosion. So, that is why we want to keep it separate, because there is some sort of chemical activity of the materials are coming into picture, and there is some sort of properties of electrolytes are coming into picture, and then industry has some sort of we say the more application of galvanic corrosion. So, we will try to keep this in a separate category. Now, in this case what we metals are same, in this case what we have thought about aqueous corrosion. You see in this case also in the galvanic, one metal operates as anode and other metal operates as the cathode, and then metal which is operating as anode get oxidized or get corroded, start losing the material, while cathode will be receiving the electrons, and then it will be kind of continuing, or maybe they are trying to make some sort of a conductivity in a whole cell as such. Now, to summarize, I can say that aqueous corrosion can occur without presence of second metal, while galvanic corrosion cannot. So, galvanic corrosion necessitates the presence of the two separate metal and alloy, and that is why I am giving these two in a two separate category. I do not want to keep in the same category. Then comes the aqueous corrosion is caused by chemical properties of environment. So, more emphasis is generally given on the chemical properties of environment as such, whereas in galvanic corrosion we want to give more emphasis on electrochemical potential difference between the metals and the somewhat the presence of the electrolyte. So, here more emphasis will be given on the metals or materials which have a potential difference, while in aqueous corrosion we will be giving more emphasis on environment. So, these are the some differences, that is why we want to keep in a separate category. Let us look at what is the galvanic corrosion in overview. We say galvanic corrosion happens when the two different metal or materials alloy with a different electrochemical potential. If they have the same electrochemical potential, I will not keep in this category, or they have a very marginal difference, we will not keep in a galvanic corrosion. There is some difference, so then that is why we say that there is we want to keep in a separate category as such. When they come into the electrical contact, because there is exchange of the electrons, the way in aqueous or same thing, but we are using the word here electrical contact with each other, and there is a presence of electrolytes. So, we say galvanic corrosion happens when the two metal or alloy with a different electrochemical potential come into electrical contact with one another while electrolyte is present. When these different metals are coupled, they are made in kind of the battery unit, the electrochemical cell is created, causing electric current to flow, right. So, these are the important for us. Of course, in rust also same thing happens, corrosion, aqueous corrosion also same thing happens, but we want to give in this more weightage, reason being the two different metals, right. Now, here we are saying to differentiate that the more active, less noble, we are trying to give a degree what kind of activity and how more active is this. So, more active less noble metal will corrode as a result. So, only one metal. Now, suppose there are a number of materials available, and some materials are cheaper, some materials are costlier, or maybe when we make a complete structure, we know one interior part is more difficult to remove, and when top surface is easy to remove. So, I can change this kind of I can make this galvanic corrosion from that to save inside material. I can make a outer surface less noble, and so the complete corrosion will occur on the outer surface, which is easy to replace, which is visible to us. So, that kind of science can be utilized and we can design in this manner. Now, in this case another one important comes the galvanic corrosion when we are talking something like a shape of the surface and microstructure. So, shape of the surface as well as the microstructure have a big impact on a galvanic corrosion. Try to explain this what I mentioned here. Let us take this figure, maybe say fig 1 and fig 2, and there are what we are showing cathode and anode is reversible. Here whatever is the cathode we are making anode, here whatever anode we are making cathode. So, in this case what we say large anode, small cathode area showing relatively insignificant attack. That means there are the bigger size of anode is a preferable compared to the cathode. If this ratio anode area by cathode surface area is something like a 3, 4, 5, 6, 7 something, it will be always preferable. Now, coming to the second situation, we say anode is smaller, cathode is much wider, something like that. So, large cathode area, small anode area showing a relatively pronounced attack of the fastener head. In this case we are showing, that means the corrosion of this head will be very high, right. So, naturally now when we know the science, which surface should act as anode, which surface act as the cathode, we can play and we can really design according to that. So, if I try to summarize this, we can say relative surface area of the two metal in contact affect the galvanic corrosion, important. Another one is a microstructure. As I mentioned, the microstructure of metal surface has an impact on how corrosion forms and spread also. So, if there is a corrosion, it will be formation and how the form it will be going to spread. Now, here we can say very clearly surface imperfection like scratches, cracks, roughness, that is going to increase the localized corrosion. If you want to keep surface very good or maybe say free from this kind of scratches or cracks or roughness, then it will be having a lesser chance of corrosion. And the same thing we have studied in wear phenomena, and then the same with the friction also. Keep a surface very good, almost a nano level, wear will be reduced significantly, corrosion will be reduced significantly. So, whatever additional cost or additional manufacturing cost can be compensated will be kind of we spend 1 penny and we get a benefit of the $1, something like that. So, this is what we really require. To understand slightly more in detail, I am trying to cover this slide what we say galvanic corrosion. I am trying to highlight. This is the ionization process occurs at the top atom. At atom we mentioned that atoms are atoms which are on surface, on the metal surface or edges, because reason being that these atoms are loosely connected with the internal structure. So, this preference is because atoms are bound to be fewer adjacent atoms connection or maybe the bonds are lesser with the subsurface atoms, making them more sensitive to ionization. So, what I mentioned here is that ionization happens only on atoms which are exposed, which has a lesser the binding with the other atoms. So, that is what has been mentioned. Now, any impurity, presence of impurity acts as a catalyst. So, it makes the corrosion phenomena, or it can enhance the corrosion phenomena significantly. So, we say that it acts as a catalyst for the reaction and speed up this process. I am just trying to show one of the example to indicate that. Here we are using the word grain boundaries are there, maybe you are showing the 3 faces of the surface, top and then the front and maybe side. Now, here if you want to just keep a graphene flake on a copper surface, something like a graphene flake can be kept on a copper surface. As such, copper has some resistance, but now graphene comes, it is going to create some sort of a localized defect. If there is a localized defect, it is going to give a, because graphene has a good wettability towards it can absorb water easily, and then if it absorbs the water, it is really going to give ingress of the water to the copper inside. So, copper will not be able to resist, and then there will be phenomena to change it. Now, if there is a phenomena like that and there is some other metals or the kind of what is a galvanic corrosion is available, then because these are going to create a local defect, or if there is some sort of vacancy. So, either we give some path because of impurities, Like in this case, I am using the word graphene flake on the copper as a kind of impurity, or there is some sort of vacancy. Then this the transformation or the shifting of atoms or maybe atom ions are easier one, and that is what we say that then the reaction will place a much faster rate and the corrosion rate will increase. While in this case there is a possibility of the selective corrosion also, wherever if you want to have some vacancy, we can create also and then make the selective corrosion. So, there are possibilities like that. Now, to explain this in more detail, I will just take one reference, and in this case what we have shown here something like the figure A, B and C. In this case, whatever I mentioned in previous slide, that the copper and there is been showing here partial oxidation of copper at the graphene flake edge. The graphene is giving some sort of the conducting path or the path to ingress the water inside the copper, and that has been shown here. Now, here what we are saying, this is the some sort of H which has been shown here, and there is a cut C has been shown here. There is some sort of the patch which has been shown in this case. So, the graphene the H has been shown, which is getting partially oxidized because of the oxygen presence there, and from water it comes to the oxygen will get absorbed in this surface, while at the center has been shown also the patches are here. So, it is some sort of corrosion. Now, just to elaborate it, something like has been shown, there is some sort of these are the images, but coming to the D to DG has been shown some sort of schematic oxidation process. What has been mentioned here, the chemi-absorption of water vapor, this water gets absorbed chemically with the covalent bond on the surface, and then there is a really provided some sort of path, and then it has been shown here some sort of different colors, and these are the basically water molecules, and then this water molecules has a hydrogen. That is why we are showing that black and white is a carbon, red is oxygen, and green sphere is a hydrogen. So, we are showing here the green and red, the oxygens are there and surfaces, while oxygen inversion has been shown here. Initially when the oxygen gets attached to the carbon, and this has been shown over here, and then with the process it gets inverted inside. Once it is oxygen gets inside, that is a partial oxygen of the copper happens. So, water gets spread to the surface, and in the presence of the graphene, it allows for the partial oxidation of the copper. If we remove this impurity, that quite possible the graphene will not really affect that much to us to the surface. Now, this topic will be continued in the next lecture, lecture 10. And lecture 10 will be surface degradation mechanism due to corrosion corrosion action, and the part 2 will start with this slide and then continue on that lecture. Thank you for your attention.